In this class, we will discuss two problems on finding the angle of twist and this maximum torque, whatever it is, for two thin wall sections. So this is the first problem, wherein he has given a section like this. So this section consists of, you can see, a rectangular part and two semicircular parts. So this the length of this rectangle section is 50 mm by and width is 30 mm, and the radius of this semicircular section on either side it is 15 mm. That is diameter is 30 mm. Thickness of the tube here is given 5 mm throughout. Length of this section is 1.5 meter or 1500 mm. Thickness is of course 5 mm. And here he has given that this is the theta value is restricted to 8 degrees. So that is maximum value of theta over this length 1500 mm length is 8 degrees. So this 8 degrees should be converted to radians. So a radians, if you want to convert, it is 8 into pi by 180. So theta should be in radians. Remember that when you are substituting the problem or formula, theta should be converted into radians. This is the maximum value of theta that is allowed. And the question is, what is the value of maximum torque this section can take, and what is the value of maximum shear stress that is induced in that section? And he has given rigidity modulus G value 80 GPa, that is 80 into 10 power 3 MPa or Newton per mm square. Now we have seen in the last lecture the expressions for angle of twist and also for torque. So the solution runs like this. We have to calculate what is called as the enclosed area. Enclosed area is the whatever center line is there here. So whatever area enclosed within this center line, so that is your enclosed area A. In this case, it consists of a rectangular part and two semicircular parts. So these two semicircular parts, if you add, you get one full circular part. So the area of the rectangular part is 50 by 30 mm square, of course, plus area of circle. One full circle will be pi r square. Here you can see that radius r is 15 mm, so pi into 15 square. So we have to add these two. This is the rectangular part and this is the circular part. So if you add these two, you will get the total area as 2207 millimeter square. So that area is this enclosed area, center line within that whatever is in that area. Now we know the formula for the angle of twist. So this angle of twist is given by theta is equal to q by 2ag into closed integral ds by t. So this is the formula. Here q is called as the shear flow, a is this enclosed area, g is the rigidity modulus, ds is measured along the circumference in the case of a circular part, and it is the length and the width in the case of a rectangular part. T is the corresponding thickness of that particular part. Now here he has given this theta value, maximum value of theta is 8 degree, which is nothing but pi by 180 into 8 radian. But since the length is given, so this theta max normally it is taken as angle of twist per unit length. So per unit length means he has given 1500 mm as the length of that section. So divided by length will give the per millimeter. So this is the value of theta we have to substitute in the formula. Now substituting this in this formula, so what we get here is LHS is theta, substituting in 1, LHS is theta, that is pi by 180 into 8 divided by 1500. It should be equal to, now the RHS part is q by 2ag. So q is unknown here. We have to find out the shear flow. So q is called as the shear flow, that we have to find out. So that shear q divided by 2 into a is this enclosed area into g is 80 into 10 power 3. Please note that g should be substituted in MPa or Newton per mm square. So all the units we are taking in Newton and millimeter. You should be careful. So divided by the 2ag into, now the closed integral means ds by t. So 1 by 1 will take, here there and 50. These two rectangle portion, there are two lengths there. So 2 into 50, 2 into 50 plus 2 times pi into 15. 2 times pi into 15 means 2 pi r. So this is 1 pi r. This is another pi r. Okay. So this we have to take. So this one we have to take. So and this one we have to take. So this length of this semicircle or circumference of this semicircle plus circumference of this semicircle becomes the circumference of one full circle. So that is 2 pi r. So circumference of circle is 2 pi r. So 2 pi into r is 15 here. So this is your total ds. So this becomes your total ds here, and then divided by, of course, since the thickness is same throughout, divided by t means divided by 5. Suppose if this is having some different thickness, so for this circular portion we have to take that value of t. So you should be careful that if they give different thickness. If it is same thickness, common value of t will be there. Now if you substitute and simplify this, you are going to get Q as 846.1 Newton per mm. So this is called as the shear flow. So shear flow is actually, this is a constant. Shear flow always is a constant, and you know that this Q is equal to tau into T, where tau is the shear stress and T is the thickness. So shear stress and thickness may vary, but their product remains same. Now to calculate the maximum torque that can be applied on this section, the formula is 2AQ. Once Q is found out, so A you know, so 2 into A is 2407 into Q is 846.1. If you multiply that, whatever answer you are going to get, it will be Newton and millimeter. So finally you can substitute, can convert that into kilonewton meter. So 10 power 6 is the conversion factor. So this is the value of maximum torque that can be applied over this cross section, which is having a length of 1500 mm. And he has asked for maximum shear stress that is induced in that section. So tau max is given by Q by T. So here T is common here for all the portions. So 846.1 divided by 5, which comes out to be 169.2 Newton per mm square. So one thing you have to keep it in mind. Suppose if they have different thickness, then tau max will be given by Q divided by T minimum. Please note this. Suppose if this has 3 mm or if this has 3 mm, one may be 3, another one may be 5, then you have to take 3 mm here to calculate the maximum shear stress that is induced. Because when you take T minimum, denominator is minimum, so therefore the answer will be maximum. So this is how we have to do the problem of finding maximum torque and shear stress. Another problem of same kind, of course, but the cross section is a triangle cross section, right angle triangle cross section. So they have given the lengths of these center to center lengths of these three edges as 30 mm, 40 mm and 50 mm. Of course, thickness T is uniform 10 mm throughout. So T is 10 mm throughout. It is having same thickness. Length of this cross section tube of that tube is 2 meters, that is 2000 mm. So he has given here maximum shear stress itself. So tau max he has given. You are asked to find T max and theta. So what is the maximum angle of twist that can be that you can observe when this member is subjected to torque like this. Now, of course, G value, of course, different material, 50 GPa has given 15 to 10 power 3 MPa Newton per mm square. So same procedure is used here. Since he has given here tau value, so tau value he has given. So tau into T, this is the first step here. Tau into T we have to calculate, that gives the value of Q. So this is the shear flow. That is 50 into 10. So this value is 500. 500 is the shear flow. This is a constant value. So which is the same in all the like this. So that means shear Q value will be same. Shear flow can be shown like this. So this value is a constant value. So 500 Newton per mm, and the enclosed area. So center line, you know the center line. Enclosed area is a triangle portion. So half into base into height. So that is half into 40 into 30. which comes out to be 600 millimeter square. That is this enclosed area. And Tmax you can directly find out using this formula 2A. Once A and Q are known, so 2 into A is 600 and Q is 500. So you will get 0.6 into 10 power 6 Newton millimeter, or you can write it as 0.6 kilonewton meter. So this is the maximum torque that can be applied on this cross section. Now theta, to find theta, what we have to do here is the formula is once again Q divided by 2Ag into closed integral ds by t. So here we have found out this Q 500 Newton per mm divided by 2 into A is 600 and G is 50 into 10 power 3 here into this closed integral ds value is nothing but length. So length on all the three sides and T is the thickness on all the three portions. Now here since it has got uniform thickness 10 mm, so this first I will take this 30. So ds is 30 here divided by 10. T is 10 plus ds is 40 here divided by 10. ds is 50 here divided by 10. So this is 30 plus 40 plus 50 divided by 10. So that gives the closed integral ds by t value. And if you simplify, you are getting 0.0001 radian per mm. Please note that this whatever theta is there here, so this value it will give in radian per mm per unit length. Here unit length is millimeter. Now if you want the total angle of twist for the entire length, so we have to multiply this theta by the length, that's all. So this is per millimeter. If you want to have for entire length of the section, then you have to multiply by the length. So 0.0001 into 2000, length 2000 mm. So that means it should be converted to millimeter. So you are going to get 0.2 radian as the total twist. So total twist of the bar. This thing. For example, that means it is like this. So suppose if the section is like this. So if the length is 2000 mm. So this length is 2000 mm. So for 1 mm, the twist is 0.001 radian. So maybe for 1 mm. So let us take this is how we have to interpret. 1 mm is this length, let us say. So here the twist is this much, 0.001. If you take for the entire 2000 mm, so we are assuming linear variation. So this is the value of 0.2 radian. So this is how we have to show the twist. Here this is 0.0001 radian. So it will give on one end it is 0.0001 radian, and the other end it is 0.2 radian. So this is how we can find out the twist, total angle of twist for the entire length. So in one problem he has given theta value and he has asked to find maximum torque and maximum shear stress. In the other problem, he has given maximum shear stress and he has asked to find the maximum torque and the angle of twist. So angle of twist is in this formula. We are going to get angle of twist per unit length. If you want the entire angle of twist for the entire length, you have to multiply the value of theta by the length of the section. So this is what I wanted to explain.